So, can you start, sir?
Yes, yes.
Welcome to online short-term course on power electronics converter application in microgrid and vehicle technology. Day 3, session 3. This session will be a tutorial session, will be handed over by Rajesh Kumar Lenka, a research scholar from NIT, Department of Electrical Engineering, NIT Rourkela. I welcome Rajesh Kumar Lenka, sir. Please hand over the session.
Thank you, Allu. Rajesh Kumar from Department of Electrical Engineering. Am I audible?
Yes, sir, you're audible, sir.
Okay. So I'm Rajesh Kumar Lenka. I'm a research scholar, PhD research scholar in Department of Electrical Engineering, and I am working in electric vehicle chargers, that is multi-functional chargers. But now today I will go to present the basic brief and overview about the electric vehicle charger scenario in this world. So my topic is electric vehicles battery chargers topologies, charging power levels and infrastructure recently in this world. So I will go like this. First I will give introduction about my topic, and then we are going to see the overviews of electric battery chargers. So in that I will categorize the chargers as two types, that is unidirectional and bidirectional chargers. So the other categories I will discuss in this section. Then I'll go for the multifunctional bidirectional EV chargers, which we have doing in research in my power electronics laboratory. That is my PhD work. And then we integrate the EV chargers with the solar PV, that is the renewable energy based EV chargers. Then some proposed operating modes of the EV chargers. Then I will go into show the results and discussion sections. Then we will conclude the topic. First, we will go for the introduction. So why EV is so much getting attention in this world? Because of increasing environmental pollutions and limiting petroleum fuels resulted in two significant changes in this world. The first is we are adopting renewable energy sources in place of conventional energy sources, and the second is we are replacing the conventional energy based vehicles by adopting electric vehicles. So according to this, in the world scenario, the US is officially domestic global putting 1 million EVs on the road, and they have targeted in 2015 they will put 1 million of EVs in their road, and they have succeeded in that. So in India also the government is providing subsidies and encourage the people to adopt EV. So nowadays, after the COVID, the importance and the popularity of EV vehicles and EV four-wheelers and two-wheelers are getting so much attention, and government also encouraging by providing subsidies, and that also decreases our pollution level. So to go for any worldwide EV sections, so we need some standardizations to put the chargers technology and charging technology. So much organizations are working on the standards, like IEEE Society Automatic Engineers, SAE, which we are familiar about that, and the other is IWC. They are preparing the standards and with respect to the utility and the customer interface. But why the EV is now, means there is some barriers which the EVs electric vehicle has some barriers. That's why nowadays combustion based engines are more than the EVs. This includes I divided into three main categories, that is the high cost and the life cycle of batteries. So EVs are high costly, and the distance, the range we didn't achieve that much of range till now. and lots of research is going on. So in future we will definitely achieve. So and the cost is very high with the life cycle of the battery. So recently so much news came that the batteries are burst out due to heating effects. So lots of experiments and research are going on. And complications of chargers. So basically we are working on chargers, but availability of chargers in all the cities and everywhere is not till now it is not available in India. In urban countries it is there, but lack of charging, that is going on, the lack of charging infrastructures. So these are the main barriers to means we have to overcome to increase the EV utilizations. So another drawback is that if you are integrating the EVs, so the as it is the charger is consisting of the power electronics converters, so it can produce the deleterious harmonics effects due to the nonlinear effects and the electric utility distribution system. Although chargers with an so the harmonics harmonics is there. That's to so we are preferring the harmonics with active rectifier or active filters, so that the current quality, power quality of the system should maintain. So these are main introductions. So I talked about the barriers and what happened if we increase the charging systems and now recent standards. Then we will go for the okay. So now we will talk about the EV charging standards and the charging levels and types of chargers according to the power electronic circuitry like this. So first I will go by the levels, the types of chargers by the levels, that is the power level. So most of the EV now recent trends, most of the EV chargers are we are charging in the garage in our home only. So this is basically a slow charging system, and that is taking 8 to 9 hours to charge. We are putting our vehicles in the garage in the night, and in the morning we can use it. So that goes under the level 1. And then the level 2 charging is basically it is can be private or public. So the voltage range are given in the table number 1 and voltage and everything. And it can be public and it can be private also. And the voltage level is 220 volts. And the level 3 is the DC fast charging system, which we are working in and intended for commercial public application, like the fuel stations are there, petrol pumps like this. You can use this level of charging to create the charging stations, EV charging stations. So like I have written also there, the operating like filling stations and three-phase solutions normally applied. Basically we are using CPS. The charging power levels are summarized in table number 9. That table like is given. That is the level. US means United States and EU means European Union. So in level 1, that is 120 volts AC in US and 230 volt in European Union, and this is the onboard. So again in the next slide I will discuss what is onboard and offboard. So there is categorized in the another categories, that is inside the car the charger is present or outside the car. So basically the fast DC chargers are offboard three-phase chargers, and they are basically commercially used and like a filling stations. And the power range is 50 kilowatt and 100 kilowatt, and charging time is very small, that is 0.4 and 1 hour. So basically the most of the plannings are happening to place this level 3 chargers in the NH, that is the NH corridors, so that EV can be get some range extension. So this table is basically I have adapted from a reference number 1, which I have given in the in my reference section. Okay, then EV charge is going to be then I talk about that the onboard and offboard. So onboard means the charger is present in the EV only, and offboard it is the outside of the EV. Only the mechanical part will be in the EV, and the charger can be hybrid also. So according to the onboard and offboard, it can be unidirectional and bidirectional power flow happens. That depends upon the power electronic circuitry of the charger. So unidirectional charging is logical faster because it limits hardware requirements. So unidirectional, there is not much hardware requirements is there, and it simplifies interconnections issues and reduces the battery degradations because the discharging is not visible there, and also its low cost is very low. But in bidirectional charger, so it supports two-way power flow, that is unidirectional and bidirectional. So that is from grid to vehicle, it can charge and it can inject the stored energy of the battery of the EV when it is not used. can be utilized for the grid, for local load supply. That is called V2G, vehicle to grid operating modes. In later we will discuss all about this. And this can be also used to power stabilizations, improving grid power quality, providing grid ancillary services like frequency stabilization, voltage stabilizations, reactive power support. So bidirectional chargers are much more applications than unidirectionals. So typically onboard chargers limits high power. In high power applications, onboard chargers are not feasible because the size will be very big and the car size will be very high. So we'll go for offboard. So we are basically working on offboard chargers. So according to onboard and offboard, we are going for offboard chargers. And for unidirectional and bidirectional, I have given all the in table number 2 a comparison between their in which level of application it will be there and power applications, which type of converters is required, isolated or non-isolated. So unidirectional, only one way power flow is there, that is G2V. And for high power applications in bidirectional, IGBT will be medium power. For high power application, we need GTO. Like all these classifications, I have presented there. So in unidirectional, you can see the battery effects, no discharging degradations. But in bidirectional, degradation due to the frequency cycles, because we can use the stored energy by V2Z operating modes. And it can be used for ancillary services like I have discussed there, that the voltage regulations, frequency regulations, spinning reserves, reactive power supports, peak saving. Peak savings means at the peak hours, the EV stored energy can be supplied to the local load, so that the peak time the conventional power source will not be affected, and energy balance also. Like this, I have classified all these unidirectional bidirectional applications. So as you see, the bidirectional chargers are more applications than unidirectional. So we have adopted offboard, and in offboard I have adopted the bidirectional chargers. So next we will go to some configurations already present in the literature I have presented here. So that is the interleaved unidirectional charger in figure number 1 and figure number 2. It is a unidirectional multi-level chargers, and in figure number 3 I have given 3 types of bidirectional chargers. So these are the bidirectional charger in the charger configurations. Then this is the basic structure of deployment. So as I have discussed, this level 1 and level 2, you can see onboard charger. Onboard charger is there, and there is a home garage office charger is there, and offboard charger level 3 charger is there, and that is grid. So 3-phase supply, 3 lines are there, and this is the onboard application level 1, level 2, and this is the level 3, and this is the charging. So the onboard and offboard battery charger, that is the bidirectional battery bank, and this is the motor, and this is converter, this is converter, and this is the battery pack.
Yes, sir. So can I continue or?
Yes, Rajesh, please carry on. Yes.
So this is the basic structure. I have implemented all the chargers and possibilities, and this can be the hybrid charger also, and all the mechanical part and electrical part. But we are basically working on bidirectional offboard chargers. So next, I see some of the connecting structure should be there. We should know the DC level 1 chargers, and these are the countries and which standards we are using now. So we are basically working on developing our control and everything for CHS demo chargers, because it has a communication channel, and basically I will show the pin diagram. So in 5th and 6th pin is used for charging, and 8 and 9 for communication, so we can control, and bidirectional power flow is possible, and renewable energy integration is possible with this charger configuration standard. So this is the pin diagram. So we are basically developing by considering CSDMO chargers. Okay, for next, I have given some of the charging topologies already adopted by some companies, that is the Toyota, Chevrolet, Mitsubishi, Nissan, and Tesla, and their power level and charging standard connector, that is SAE J1172, they are adopting. and charging times, DC fast charging available or not. These are the basic overview and the literature for the available chargers in the market. Okay, then we will proceed towards the basic power electronics part, that is the converter parts, and in unidirectional, which are the converters is possible, what are the properties and their comparisons in bidirectional. Basically, I will not describe the unidirectional as we are preparing the bidirectional. So, so the converter should be grid. There are in next slide I will properly explain. So basically, it can be the converters can be the grid facing converter, can be half bridge, full bridge, multi-level converter, voltage source or current source, and matrix converter. So basically, I'm warning that the multi-level converters are more advantageous for medium and high power applications. I'm saying that medium and high power applications. So the reasons I will describe later in the next slide. So these are the basic half bridge, and that is epi converter, to converter, DC-DC parts that I am saying. That is half bridge, and full bridge more component PW. That is a comparative study. It is present, and in with the multi-level requires additional control circuitry, but additional component increases cost and complexity. But lower component stress and losses is there with the multi-level. So due to less component stress, so high and medium power application it will be feasible. So efficiency will be high, and reduce size and switching frequency also low, and it's EMI, so EMI noise due to there. It will be advantageous for grid integration. So the topology we have developed from multi-level I will discuss in the next slide. So I think it is repeated. Okay. So this is basically the charging configuration. So I wrote this residential load means this is a charging station load. Okay, the charging station nowadays the charging station can be a shopping complex or anything. So it should have some load, light load, AC load like this. So there are two converters. First is the grid converter, and second is the AV converter. This is the AC-DC part bidirectional, and this is DC-DC bidirectional, and this is the EV charging. And power electronic circuitry it is given in the below, that is connected to the grid, and there is a load, and this is the converter fronted AC-DC CSB-DC converter. I have named it our topology. So I will discuss later what is this. And this is a conventional bidirectional back-end bidirectional DC-DC converter, and this is the EV battery charger. So this is the basic diagram of our converter topology, which our cascaded H-bridge bidirectional converter, which is 7 level, and this is the bidirectional converter, and this is the charger, and this is the load, and this is the grid, and we connected the bidirectional switch so that we can change the operating mode from the grid connected operation to any grid failure occurs than standalone mode. So why we adopted the cascaded H-bridge bidirectional converter, which I have showed you in this conversion, not conventional VSC. So what happened in the low level, in the low voltage levels, that is the topology reliability is not much more concerned due to the repairing time is very low, the converter size is very low, and the financially the expenses will be low. But in medium and high power level, the unavailability of converters may cause high revenue losses. Therefore, the reliability of the converter is higher priority over the cost in medium and high power applications. Moreover, in the applications like which I have given there, that bidirectional converter we can provide the grid ancillary services and the grid services like reactive compensation, harmonic compensations, so that it's so to achieve all these things we need some voltage level at the DC link voltage. So according to the standard, it should at least 10% higher than the peak grid voltage. So for medium and high voltage applications, the multi-level converter is a must, because if the DC link voltage will be high, the voltage stress across the conventional two-level converters, the voltage stress across the switches will be very high, so that the volt breakdown will be may occur. That's why the multi-level converters are most prominent. Then due to decreased voltage stress across the converter leads to premature dead on the converters, that I given the reasons. So among the VSC technology, that is the low voltage applications, two-level voltage source converters are most early adopted, and it is cost efficient also. And then going forward, the 3 levels NPC, neutral point clamp converter also we are adopted, but cascaded H-bridge multi-level converters has added advantage over these 2 topologies, that is the neutral clamp and high capacitors. Due to the high dB by reduced dB by dt stress, low component count, high reliability, soft switching capability, like this. However, the major disadvantages then among the cascaded H-bridge multi-level converter, it also has some disadvantages due to the each module should have an independent DC source. So this increases control complexity and voltage measuring sensor count. So to resolve this problem, we have adopted this conventional CHV multi-level converter combination with single DC source, which I have showed you that we have adopted the single DC source, that is the cascaded H-bridge structure, instead of adopting individual independent voltage source for each H-bridge. So some other advantages I have adopted for CSBTC is the usage of the, as we are using the transformer in the circuit, transformer circuit is there, that the transformers are cascaded to give the phase voltage. Transformer, the harmonic reduction capability of the system improves significantly. These transformers also provide the galvanic isolation between the AC and DC system, so that any fault in the AC side or load side does make the system more highly reliable, and the proper system structure can easily be the proper system structure can easily be coupled to the grid and utility interfacing applications and have less electromagnetic interfaces. The cascaded transformer-based topology performs well even with low power semiconductor switches. So these are the basic advantages. So I will not go deep on that. So let's discuss about the. So from this we conclude that we have adopted a bidirectional off-board EV chargers with the grid converter. So grid converter. So this grid converter is a multi-level converter with cascaded HBs with galvanic isolations, and EV converter is a DC backend bidirectional converter. So this is the basic structure. Now I will go for our works, that is the which operating modes I have proposed. That is the operating modes. First is the grid, this is the electric vehicle, and this is the load, and this is the PV. So figure 8 shows that it is the G2V mode. That is the battery is taking power from the PEV. The power is given to the battery. And next, in figure number 9, I have shown the V2G operating mode, that the reactive power is poured to the grid, that is the battery is supplying to the grid. Then I have proposed, I have working on the reactive power compensation. The grid converter, grid facing converter, I have the control technique is developed so that it can provide the reactive power compensation. So before reactive power compensation with G2B, battery is charging. Along with it is providing reactive power support in figure number 11 it is. So load is demanding some reactive power, so the voltage and current are not in phase. But the converter control, the grid facing converter control enables is the unity power factor, and it is happening in G2B without reactive power support. But now what happened, the grid facing converter of the charger providing reactive power and making the grid current and voltage unity power factor, and providing some reactive power according to the leading or lagging, depends. So this is the one operating mode, that is called reactive power support by reactive power compensation operating mode. Then grid current harmonic, as I am saying, so many chargers are there and they are imposing harmonics into the system. So the grid current is harmonically distorted, but so that you are using basically the active filters along with the chargers. But now there is no need, which improves the cost. So why there is extra power electronics equipment will be there, so whose control expenses and whose maintenance also costly. So instead of using extra active filters, we can control the grid facing converter to improve the grid power quality, which operating mode I have named as the grid current harmonic compensation operating mode. And you can see the source current before the compensation is harmonically distorted, and after the compensation it becomes sinusoidal, and according to the current changes, all current changes. So this is the experimental model, experimental structure which I have used, and this is, you can see the cascaded transformer, HBs transformer, that is the transformers, each HBridge, this Lenka, CHBDC and control, and this is the VDDC converter, battery unit, and this is the cascaded HBridge. This is the load we have used, and FPGA control we have achieved, and all the measurements by DSO and test supply is there. So basically, this work is published in our one of the paper that I given here. So for details control circuit and detail analysis, mathematical analysis, you can report this paper. So I will not go deep into that modeling part. So I will basically describe only the overall view, and we will go for the simulations. So this is our experimental model, which are only. And the results I am showing, these are the results I have get that is the grid voltage and grid current, ICH and IER, before compensation ICH, and these are the measurements. Before compensation, the current TSDs are 26 for phase A, 26.953 for phase B, and 27.291 for phase C. But after compensation, you can see in the figure D, the ITSD lies below 5%, that is 2.3 and 2.5 and 2.5. And I have, that is C4G means charger 4 grid. So I have proposed the reactive power compensation and grid current harmonic compensation in the charger for grid operating mode operation. The two categories are there, that is the reactive power and grid current harmonic compensation. So you can see after the grid current harmonic compensation starts, the grid current becomes sinusoidal with lesser harmonics. So it can be achieved by controlling the grid phasing converter, that is a CHVDC multi-level converter. And now, so reactive power supply, which I have discussed, that the reactive power support that C4G RPS, that is lagging, leading, and according to that, the current and the EV current, EV charging, EV discharging, G2B mode, E2G mode, and according to the current and voltage of the grid, of the charger, of VCC, I have shown here. And next is that I saw that if the EV is possible to give G2 transform between the G2B and V2G operating modes, then what happened? That also I have saying that previously it is in phase G2B, then again it is go to V2G, then it will be 180-degree phase shift that I saw in figure number 16. And again, after that we'll go for the so it is till now we are not integrated the renewable energy system PV to the grid, because grid is the primary, where EV it is not there. The PV is means renewable energy is not there. So basically we are working on only the EV and grid, integrated to the grid. Charger is integrated to the grid, but not the solar system. So now in the next work, what we have here, we have integrated the solar system like this. We change the part, that is the renewable energy introduced into the charging system, that is the PV. The PV converter is there to achieve the basically achieve the MPPT, EV converter and energy storage system I have integrated. So the reason for energy storage system we will discuss later. So this solar integrated EV charging, bidirectional charging, this work also published in industry application work. So for control and details analysis, you can refer this paper. So next we will go to the overview of these chargers and how we concluded on this. So this is the basic each and every converter I have discussed. What is the literature I have developed this. So previously what is there? Previously PV converter, grid converter and EV converter. There are 3 converters are there, and PV is integrated to the DC link of the charger. Okay, by through the PV converter. The next improvement what happened, that we removed the PV converter and the MPPT is achieved to the grid converter. So that what happened? So that one control converter is reduced, cost is reduced, control complexity will be reduced, and no need to control one another extra converter. So that is possible if grid converter can do all these things. So there is no need to integrate the PV converter. So next modification what they did. So as the EV converter, EV this requires the for stabilization, EV is always should be connected to the grid. So any energy PV solar irradiance changes or any intermittency in the renewable energy system. So it requires energy through the grid. So battery charging and discharging cycle should increase which dead state is lying. So what they do in the literature, they introduce the energy storage system. So energy storage system is again a battery, and it is integrated to the reselling through the energy storage system. And then what happened? Then again, what we have proposed, we remove this PV system, and grid converter is there, and this is our proposed system, which we have worked in the next work. That is, so this is basically the power grid circuit. So no extra, only the EV and energy storage system is integrated to the system, which you can see. There is no change in the converter topology, and again the load is the non-linear load, and again the bidirectional switch is there to change it to the standalone and grid connected mode operations. So this is the basic power converter, and instead of using the real solar, we are using the solar simulator. And about the solar simulator, in the previous tutorial is there, Mr. Akireti sir is also working in our lab, and he gave details about the solar simulator. So we have solar simulators. So you are using the solar simulator to emulate the PV characteristics. So basically, there is not big differences. Only the solar and energy system we have introduced into the system. So with this, what happened? Basically, we have controlled the grid facing converter. That is the CHVDC to achieve grid current harmonic compensation and reactive power support, provide reactive power support to the grid along with charging and discharging the EV batteries. Along with this, what we have did, we have controlled the bidirectional switch for easy, smooth and seamless transition from the grid connected mode to the standalone mode. So any fault occurs in the grid side, the control of bidirectional switch and control of the VSC can achieve the synchronizations as fast as possible with seamlessly and smoothly. So this is the new thing we introduced in this one. So so this is basically, you can see the VG is the grid voltage and IT is the grid current. So and this is the load current, that is IR, the load current, and you can see the grid current is improved non-linear to linear. Sorry, that is the sinusoidal, harmonics distorted to pure sinusoidal, and the values are given here. So the improved current from 22 to 3% ESD, and this is the PV output powers, that is 25 kilowatt. And these are the harmonic that is I told you about the reactive power support. So here it is providing unit power factor, then leading bar, and the lagging bar, reactive power support. And if EV will be disconnected, then what will happen to the system? And decrease in grid current, that is EV connected to the PCC, suddenly EV removed and EV connected. And residential load, that is the load I have considered for the charging station load. That is what will happen if there is load change occurs, then what will happen to the system. And what happen if the EV is charging to goes to the discharging, that is the B2G operations. So our solar is integrated to the system, so we have to analyze the system with decrease in solar irradiance and increases the solar irradiance and intermittency in the solar system. So according to that, on solar irradiance decreases, there is not much battery charging on non-retrofitted charging, but the grid current will decrease. The power fed to the grid is decreasing. So now battery is charging to discharging. Battery is moving charging to discharging. Then what happened? And like this, in standalone mode and grid connected mode, everything we have discussed. And again, we will go for this synchronization part, which I have told you integrated into the system, that whenever the system is moving from grid connected to standalone mode, that here is the grid removal occurs, and here is the grid again removed to the system. So the zoomed images are given here. GCO means grid connected operation and SO means standalone operation. So at grid current will be 0. As grid is not there, not connected, the current is 0. Then the charger will provide the current to the residential load. You can see the changes here. The charger providing the load and charger providing the load. Then again grid recovered, and grid recovered. Then the control of the CHBDC try to synchronize with the grid voltage, and it will take 4 to 5 cycles. Here you can see the orange one is the grid voltage, and the blue one is the our CHBDC output voltage, which is synchronizing by comparing the phase and frequency error. And after 4 to 5 cycles, it completely synchronized. But after synchronization 10 to 15 cycles, we have again connected to the switch, bidirectional switch SW, and the grid recovered and grid synchronizations, of course. Then grid current is 0, and again connected on the GCO mode, and normal operations happens. So basically, I will conclude with this that the battery performance of the EV not depends upon the battery type. It also depends upon the charger characteristics and charging infrastructure which we are using to charge the EV. And battery infrastructure and charging power levels are categorized into 3 types, that is level 1, level 2, and level 3. And according to the onboard and offboard charger, the power electronic circuitry you are using, the charger can be unidirectional or bidirectional. So unidirectional chargers are less costly and they have limited hardware requirements, simple and easy to use. But bidirectional charger supports battery energy injection into the grid, that is the B2G operating mode. So in the proposed work, what we have proposed in the new operating mode that I told, that's a charger for grid with the grid current harmonic compensation, charger for grid with reactive power support. These are the 2 operating modes, and grid to vehicle and vehicle to grid operating modes, which I have show the results. And then the obtained results, grid current harmonics is always less than 5%. And it improves the power quality of the grid. That's power quality of the grid by reducing the harmonic content of the grid current, which is in the introduction session I told that is the consequences of integrating the charger to the grid, which we have solved by efficiently controlling the grid facing converter. Then charger controller maintains a smooth and seamless transition from GCO to SO, which I have showed here. Smooth transition can possible, and the B2G operation can maximize the utilization of the EV battery, as it at most of the time the EV is in the parking stations only, because at the office parking station or shopping mall parking stations are in our home also. So lots of time it is placed unused. So better to use it with the grid and maximize its utilizations. These are some important references which I have referred for my work, that presentations. And thank you for all for your present listening. And if any doubts, you can ask me.
I think there are no doubts from the participant side, sir. Thank you, Rajesh, sir, for your session.
Okay.
Sir, I have one doubt.
Okay.
Yes.
Yes, sir. Hardik here. Sir, as far as power quality improvement is concerned, means I am working on power quality, but it is on distribution side. So I am using custom power quality devices. So there are 2 questions. First is that same power quality devices can be used for this EV charging application as well. And second question is that what could be the limit of the controlling device? I mean to say, in your case, you have FPGA, then we have Opal RT, then we have FPGA. then microcontroller. So what could be the better prospectus as far as power quality improvement is concerned?
Okay, so you are basically want to know that should we require any power electronics improvement devices along with EV charger?
Yeah.
Am I right? Yes. So yes, you required, but that I told you previously. So in the introduction part only, I introduced that the integration of EV will introduce the reactive power, but along with active rectifiers and sound active filter you can also use, or STATCOM also you can use to improve power quality, but it will increase the cost because you have to integrate another device. So as your grid facing converter control is able to improve the power quality, so it's good. No? So it will reduce the cost. Instead of using additional equipment integrating into the circuit. So with the charger only able to do that by controlling the grid facing converter. So I think that will be the better way.
And sir, about
the control circuit better, so this depends upon the availability. So as you are saying, the circuit, everyone doesn't have the same control part, because if the space is available with you, FPGA is available with you, OpenLT is available with you. First, what we have did that we did the simulation part first, then we confirm our work with the OpenLT, then we control our converter with the D-space. Then for portability, we move to FPGA. So now we are controlling with FPGA because it will smaller size, high switching frequency, and good controllability. So for my suggestion, according to me, if you want to work, then work in FPGA or any DSP circuit, because the displays will be very large in industry applications or anything. You need small size.
Yeah. Okay. Thank you.
So the control that depends on the availability. So if you have all these things, then learn all these things. That will be good.
Okay. Thank you.
Any other questions? So I know. So what? Any questions? Or
I think there are no more questions from participant side, sir. Thank you, sir,
Okay.
for the valuable session.
Should I stop sharing or what?
Yeah, you can stop the sharing, sir.
Okay. Thank you.
Thank you, sir. Thank you very much for this session.